Welcome back. We're ready to start the last section of Chapter 8, which is talking about polar bonds and molecules. So, what is bond polarity? And we haven't talked about it yet, but let's talk about electronegativity values and how that determines whether or not it is a polar bond. And what does a polar bond do for us? So, covalent bonds are different in terms of how the atoms are held together, how they share those electrons. Because it's two atoms, they may be the same or they may be different. And if they're different, how are they different? So the character of the molecule depends on the kind and number of atoms joined together, and these will help determine the property of that molecule. So I think of it as kind of a tug of war between the two nuclei over that pair of shared electrons. If the two atoms are the same, then they will not be able to pull those electrons in one direction or the other. However, if they are different, they will be able to pull differently. So, the bonded pairs of electrons in covalent molecules are pulled between the nuclei that are sharing those electrons. When the atoms in the bond pull equally, and this only occurs when the two atoms are identical, then we get a polar or nonpolar covalent bond. So nitrogen bonded to nitrogen, hydrogen to hydrogen, oxygen to oxygen. A polar covalent bond, also known as a polar bond, is when those two atoms are different and they do not share those electrons equally. So the more electronegative atom attracts more strongly on those pair of electrons and gains a slightly negative charge. The less electronegative atom will have a slightly positive charge. And this happens with things like water. It's very, very common. The higher electronegativity value, the greater the ability of an atom to attract electrons to itself. So, hydrogen has an electronegativity of 2.1, whereas chlorine has an electronegativity value of 3.0. These are significantly different, so the bond between hydrogen and chlorine would be polar. The chlorine atom has a higher electronegativity value, so it will be slightly or somewhat negative, and that's what that little blue symbol over the chlorine means, is it's slightly negative, and the hydrogen will be slightly positive. The lowercase Greek letter denotes the atom has a somewhat or partial charge. Less than a full +1, less than a full -1. So the minus sign shows which atom is more electronegative, and it shows how it would be attracted to maybe water, for instance, because of that slight charge. If we look at this as a kind of charge distribution, the green part of this is more electronegative, and so it's going to be slightly negative. Means the electrons are spending more time near that chlorine rather than near the hydrogen. So this is called a polar bond, and we denote it with a dipole. And when you see there is we have an arrow, and it is pointed towards the more electronegative element, and we put a little cross mark on it to denote which end is positive, but it always points towards the negative element. Water also has a dipole. This gives us so many properties of water that it's very, very important. You may have learned in biology that water is polar, and that is very true, and it also helps explain its properties. So we have two dipoles, one going from each hydrogen towards the oxygen, and the net dipole would be in between the two of those hydrogens. Oxygen acquires a slightly negative charge. Hydrogen on the left and on the right are both slightly positive. So, we're going to classify bonds as being either polar, nonpolar, or ionic. Here you also see moderately polar. We're not going to use that. We're just going to lump the moderately polar with very polar. And I'm not going to be giving you a periodic table. And so I'm going to give you some general guidelines. And these need to be in your notes. And these are the two things I'm going to check for. If something is two of the same type, then two nitrogens, two oxygens, it's nonpolar. If it is two things that are close together, two nonmetals, then it'll be moderately or slightly polar. And to be ionic, it's going to be group 1 with group 7. And the only ones that are ionic would be group 1 and group 7. If I want you to tell me that it is moderately or very polar, I will give you electronegativity values. I would write these four things on my note card for the next test. There's no sharp boundary between ionic and covalent, but we are just going to call it ionic if it's group 1 with group 7, not even group 2. So if the electronegativity values increase, the more polar the bond, and eventually it will become ionic when it gets about 2.0. Identify the bond type for each of the following: nonpolar, polar, covalent, ionic. So H and N, and I would do this by process of elimination. H and F, or F and F, have to be nonpolar because of the same atom. Here we have something that's somewhat, and they're probably going to call this one ionic. They'll call this one covalent, probably moderately, and then this one would be more. Let's see what they get. So moderately for A, nonpolar for B, ionic for C, and very polar for D. Because the further apart they get, the more polar they get on the periodic table. The presence of a polar bond in a molecule often makes the entire molecule polar. In a polar molecule, one end of the molecule is slightly negative, the other end is slightly positive. The hydrogen chloride molecule, for example, had partial charges on the hydrogen and the chlorine atoms, and they are charged regions or poles, and so we call that molecule a dipole. Hydrogen chloride molecule is a dipole. Water has a dipole. So when we have something that is a dipole, when they're just put in a solution or they are randomly distributed in any direction. However, if we put them between two plates of a magnet and we put a charge on opposite charges on those two plates, now all of the dipoles will line up, the positive end towards the negative plate and the negative end towards the positive plate. They will not move left or right, but they'll just align with that magnetic field. The effect of polar bonds on polarity of the entire molecule depends on the shape as well. That's why we did that lab where we were doing molecular shape. And so here we have CO2. There's a dipole between carbon and oxygen, but those two dipoles, or those two arrows, will cancel each other out. And so it will actually have no net dipole because they cancel each other out. Water has two polar bonds. However, it is bent rather than linear. And so the two bond polarities will not cancel each other out. And water is a polar molecule. So we're going to stop here and we'll start the next one in just a minute. Thanks for listening. See you in class.